Okay. Is there still someone outside? No? Okay, let's start with the next lecture about the machine learning and signal processing. So, techniques that we actually discussed today are among the most important techniques that you probably encounter in the near future for your applications. So whatever we say today are really important. They're not all of them, but among the most important ones. So if you can learn these algorithms or techniques that we discussed today and get the intuition behind and the theoretical stuff related, then you would probably have no problem to learn about, for example, hidden Markov models, HMM models. You will have no problem in many dimensionality reduction techniques. And for density estimation methods. So you wouldn't have any problem in those cases if you can understand the interpretations and how we can actually get the intuition of these algorithms. So for this lecture, I'm going to talk about clustering methods. They are really important in the sense that in many cases you have the data which has a lack of information. One of these information, if I give you a bunch of data in a specific domain, and I give you the data without any other information in some dimensionality, then there will be a lack of information. And what is that information which is missing actually? If I give you, for example, let me pictorially, maybe you can understand it much better. If I give you this bunch of data, and this is the whole thing that I give you in two-dimensional space, this is all I give you. There is an information missing. What is that information? The information which is missing is whether this data, they all belong to the same class or they belong to different classes. So the class separability or the class labels are missing. We don't have class labels. You just have the data. But probably this bunch of data which are more close to each other, they have some relations that makes them to be close to each other. There will be some kind of information inside that we don't have it. It's a latent information. And this latent information for this kind of data, which we just see it as black and white, that missing information here is class labels. Okay? So probably these bunch of data which are more close to each other, they are somehow derived from the same class or belong to the same class. These belong to the same class, these belong to the same class, and these belong to the same class. And then there might be some kind of outliers outside these classes. And that's what is missing. So just looking at the data black and white, that information which is missing is the class label, which we don't have any information about that. Class label here is the hidden data. the hidden data or the latent data. So mostly you see in the literature latent, or it means hidden data. In HMM, for example, in hidden Markov model, you have the data, assuming that these are the time-based data from 1 to time t. In the model, in the hidden Markov model, what we actually consider is that every observation at any time is actually taken from a hidden model. So there is a state that produces this observation. And then we have transition to another state, and so on. So there is a parallel structure to this observation. This is the observation, you see it, and in the graphical model we normally hash it because it means that we have already this data, we observe this data. But there is a parallel structure to the observed data, which is called the state transition, or the state structure, or the state diagram. So that's what constructs the hidden Markov model. So the Markov model is actually constructed based on this model. This graphical model represents the hidden Markov model. So you have these states, and then for these states, even though the data itself might be taken randomly with the identical and independent distributed, so even though the data might be considered IID, so it means that every sample of the data is independent from the other one, the next or previous. But for the case of the states, it might be that they are dependent in some way. For example, there might be transitions from one state to another with some probability, or transition from the other one to the first one with some probability, and also transition from one state to itself with some other probability. But what we know is that summation of all these weights all together, they sum up to 1, because we are actually having a probability. Some of these old probabilities is actually a PDF, so it should sum up to 1. But for these states, we have some kind of transition. And what HMM does, while you are doing the learning for the HMM, one of the things that you acquire out of this learning is actually getting that transition matrix, which actually tells you if you have states, for example, S1, S2, up to whatever, then it gives you the matrix, and the elements of this matrix actually shows, each of these elements shows the transition probability from a state I to a state J. It might be from one state to itself, or one state to another. So that's how the hidden Markov model works. And that's the kind of model that normally we assign for the sequence of the data or the time series data, like the speech data. So hidden Markov models are very, and the models like this actually are very widely used in different signal processing applications. And in these cases, the state of which the data, the observed data, is actually taken from or extracted out of that state. State is a latent or hidden variable. We don't know anything about the state. So state is not observed, but the observation data we have. So we have somehow to infer the parameters of that state based on the observed data. So the lack of information here is the state that we don't know that. In the first example, the lack of information was the class that the data belongs to. Today we are going to talk about the general idea of clustering and a sophisticated algorithm called expectation maximization, or EM algorithm, which enables us to actually get the maximum likelihood estimate in the cases where we have some missing data. Either the missing data reveals itself as a case of state which is hidden or latent, or the class labels which are not available. So let's start with the idea of clustering. So the idea of clustering is written here, actually, is defined here as the classification, as a kind of classification of objects into the groups. So when we say clusters, it means that groups having the same set of properties. When we do clustering, we are actually setting the data into different groups, which the elements belonging to each of these groups, they have some sort of similar properties. And is also called as partitioning of the data set. And when we are doing that, we actually need a kind of distance measure that shows how much one data is far from another group. So if the data is far from a group, it should be somehow measured by a kind of distance. And we are in the beginning part of the lectures. So we are going to talk about what are these distances and what are those properties that we're looking for. And then we go through the most, we can say, prevalent method in the clustering, which is K-means clustering. We have different types of clustering. I'm not going to, spend a lot of time on this slide. So these are different types of the clusterings. You can just go to that. But K-means is the one that we're going to pick. And for those who are working with the neural networks, self-organizing maps, SOM neural networks are actually the ones that are the methods that are used in clustering of the data. So let's talk about K-means. K-means is actually one of the most intuitive methods of clustering. Let me begin with the example which is taken from the Bishop book. Actually, probably all of you know the Bishop, the book of machine learning, pattern recognition. So if you have a bunch of data, here is this bunch of data is actually revealed with these green dots or green points. Then you want to cluster this data into different groups or classes. You start with, for example, you say that assuming we have two clusters, if we just have two groups of data, then we assign two random points in this space of the data. Just two random points, whatever it should be, is random. Then the next thing would be to find somehow the distance between the data points and these randomly chosen centers. And we will talk about what's the distance. When we get the distance, the closer those part of the data with respect to this center, they will get the assignment for this center. So they will be labeled as here, for example, purple. And for those belonging to the red one, they will get the assignment of the red one. Then, iteratively, we are trying actually to converge to some point, actually. So the next step would be reassign the centers. So we had already this assignment. Now let's take the point mass for these class labels. So we change the point mass. So we actually somehow calculate the point mass of all the data in purple. Using the point mass, we get some other center. And for example, here is the center of this point mass with the purple color. Then for the red, we do the same thing and we get this center. So the centers are changed. Again, we try to reassign the data points to the centers based on that distance measure. By doing that, we get a new set of assignments. So these are the new set of assignments. Again, we need to recalculate the centers. We recalculate the centers and we get the new point masses here and here. And we continue again and again and again until it finishes, it stops. So there is no new assignments or there is no need for the changing of the point masses, the location of the point masses. When any of these two conditions happen, it means that you have to stop the algorithm. By doing that, we have a hard assignment of the data points to the clusters, but you have the labels for the classes. So all the data in the red, they are actually having their own label, and for the blue one or for the purple one, they have their own label. So now that part of the information which was missing, actually we have it. You got the idea. So simple. Now let's talk, after the intuitive example, the pictorial example, we can go to the algorithm. We don't need actually to talk about the history of this algorithm, but it's a iterative algorithm. And here is the structure of the algorithm, how it works. So we start from one point. We take the number of the classes as an input to this function, for example, k number of the classes. Then what we do, we try to find out the centroids, or the point mass of the classes. The point mass of the classes are called the centroids. Then we try to find and calculate the distance between each data point with the centroids. The distance is actually the Euclidean distance. So what we try to do is finding the Euclidean distance between the data points and the centroids. And if the data is multiple dimensional, so you have to do this difference, this distance for every dimension separately and then summing up together to actually calculate the general Euclidean distance. When you do that, you can group the data based on the minimum distances. So each data point is closer to either the centroid 1 or centroid 2 or centroid k. The one that minimizes this distance, the class label that minimizes this distance, is actually the label of that data point. And we go ahead until there is no object movement. This movement contains either the movement of the centroids or any assignment, new assignment, changing of the assignments. If there is no change in the assignments, it means that you have to stop the algorithm. And as I showed you how it works. So that's the idea of K-means clustering method. It's so simple. Yes?
How do I know how many clusters I can expect in the data?
Yeah, that's one point. So in K-means clustering, normally that's a problem that how can we know that how many clusters should we assign for the data? But if you start from some k, just heuristically, if you do, for example, if you assign 3 instead of 2, then you will see that the point masses are too close to each other. 2 of these point masses are very close to each other. So it means that it's probably not reasonable to take one more class and you can assign everything to one class.
So if I take a k so that if I increase k until at least until exactly 2 point masses are very close to each other, two centers, can I then know that I have found every cluster in the data?
Again, please.
You said if I take if the k is too big, then two centers will be very close to each other.
Yeah.
So if I just increase my k until I have 2 clusters that are very close, does this mean that I have found all clusters in the data?
Yeah, but it's a greedy algorithm. It's an NP hard, so you have to. The only then, you know, there are a lot of tricks that you can use, but the point is that whether it's applicable in the you know, implementation or not, you can do that. But the point is that then it would be so greedy. The algorithm would take a lot of time, and you have to rerun that, because, you know, k-means by itself is an iterative algorithm. So it means that even if you know anything about the k, if k is already mentioned, then you have to go through an iterative algorithm to get the class labels. But then if k by itself is also unknown, then it would be so greedy, and they call such kind of algorithms as to be NP hard. There are methods that they try to somehow solve this problem. So there are methods that, for example, they make an initial guess for the k, and then they run the EM algorithm and do some stuff like that. But actually, I have not seen you know, something that, you know, mostly the clustering of the data and assigning the number of the clusters is also an individual problem that people have to elaborate for. Sometimes they actually work with the patterns of the data, so they're actually looking for how many patterns they can figure out in the data. So if they can, for example, realize that there are 2 different patterns in the data, they assume that we have to look for 2 different clusters. But then, based on the k-means, they can say that, okay, if we know the k, so now we can just go to the k-means clustering and assign the labels for the data. But this k, how many k we should have, is another issue. So it's quite different problem. Number of the clusters. So the idea is just you have to remove the unnecessary clusters. And yeah, you can, for example, what you can do is just you can assign a kind of cost function for the k as a cluster, number of the clusters, and try to minimize that cost function just based on the k. For example, you can make a kind of likelihood function, likelihood of the data coming from whatever parameters, and you assign k as one of those parameters, and then try to minimize that log of that likelihood based on the k together with the other parameters. So you assign also k as one of the parameters to be minimized in that cost function. But then it would be probably, you know, too complicated to get the k. So that's something that should come as a penalty somewhere. You have to see, you know, k as a penalty somewhere and try to minimize that. But in a greedy form, what you said is right. You can just try, you know, different k values, and then the one that actually gives you the closest possible centers, you can make a threshold that these 2 centroids are very close to each other, so probably they are just coming from one class. Okay, any other questions?
Is there a mathematical proof that it will converge this?
K-means algorithm, yeah, it will converge actually, because these are called actually, these are very similar to coordinate ascent algorithms. And coordinate ascent algorithms, they always converge, but they converge to the local minimum, the local optimum, better to say. So they will never converge to, it's not, you know, certain that we converge to the global point, global optimal point, but we converge to a local optimum. And we will see that a generalization of this k-means is called the EM algorithm. So EM is nothing but the probabilistic version of a k-means. An EM algorithm is proven to converge. When EM converges, k-means definitely converges. The only difference is that k-means, as you see, is hard thresholding, hard assignment. So the data points either have to be from class 1 or class 2 or class k. They will not be able to be assigned to multiple classes. Okay? Maybe it makes no sense to assign one data to different classes, but what I mean is that there are algorithms that give this assignment with some probability. So they say that with this probability, this data point might belong to the first class, with this probability to the second class, or to the third class, or the case class.
With the fuzzy logic, from fuzzy logic,
Okay.
it's something like this.
Mm,
When one element is assigned to different classes.
well, we can discuss about the logic, which one is actually logically more preferable. Maybe the first one for the k-means is more preferable because you have to finalize your idea, your decision, to belong to the data to one of the classes. Then you have the complete data together with its class label, and then you can try to do learning. If you want to have the supervised learning, one of the necessities, the requirements of the supervised learning is the class labels. So you have to have the data and the associated classes. If you have such kind of thing, data which is labeled, then you have the training data, you can go for the test data. So for supervised learning, clustering is a requirement. And in that case, you cannot say that, okay, I probabilistically, with some probability, assign the data to the clusters. You have to finalize that in some way. So k-means, in my view, is more natural way to do that. But it's not the best way. Because if we're not trying actually anymore for, as we will see in the EM algorithm, the expectation maximization, even if it might take longer time, but finally that will try to get to the optimal point, and it would be applicable in many cases that even k-means might fail. So let's start with the new part of the clustering, but beforehand we need to have some notions that are necessary to know first, or actually to review it, and then we go directly to the Gaussian mixture model and the EM algorithm as the method, as a technique that's used in the Gaussian mixture modeling. So about the likelihood function, yesterday we talked about the likelihood prior and posterior. So the likelihood is a notion when we have the data, like the data D, which are actually the xn, a set of information. For example, here we have n number of the data samples in any dimension. It could be real dimension, RD, for example. D dimensions which are real. Then the probability of observing this data based on some parameters, which normally, if we assign a kind of a model for that, for the generation of that data D, then that model probably comes with some parameters, and the probability of this data coming from that model is called likelihood. So because the data D is already given, it's not a probability, and it's kind of function, because we have observed the D. So taking the probability over D makes no sense. So that's why it's a function, it's not a probability. Assuming that the data points are generated independently, then probability of observing the data D, the xn samples, based on the parameters of the model, that if, for example, we have a Gaussian model, that the data is generated from that Gaussian distribution, and every Gaussian distribution has two parameters, mu as the mean and the covariance matrix, then the likelihood would be, because of the independence, it would be just the product of the distribution of every sample, and it would be the product of every sample from n equals to 1 to capital N of the normal distribution assigned for a sample, with the mu and sigma. So that's called the likelihood function. This is the likelihood function with these two parameters. Normally we assume the Gaussian distribution in many cases because it's most, the computational is simpler than any other PDF. And for the case of multivariate Gaussian, that's how we represent the multivariate Gaussian data. So the PDF is actually the mean vector and the covariance as a matrix, and we have such kind of explanation of this multivariate Gaussian PDF. And the inverse of covariance is also called the precision matrix. In one dimension is actually the inverse of the variance. When we say we need to maximize the likelihood based on the parameters to get the parameters out and estimate it, what we mean is that actually because of the Gaussian property we can just use the logarithm, and logarithm is a monotonic function, so whatever solution for the logarithm is quite the same as what was for the likelihood itself. And we take the logarithm, and considering this exponential form that we see here, it would be simplified to these terms. And these terms, well, the second one actually has no dependency on the mu or the sigma, so it has nothing to do with the optimization, the maximization. So this part and this part actually you have to consider for the case of optimization, but while doing optimization we separately use the gradient of this function with respect to mu and take the other one fixed, and the other way around when we are calculating the optimum parameter of covariance, we take the mu fixed. By doing that, we get the maximum likelihood mean and maximum likelihood variance, or the covariance. And the maximum likelihood mean using this multivariate Gaussian is just a sample mean, and the maximum likelihood covariance is the sample covariance. So by having this notion of Gaussian distribution, we go and generalize the idea for the cases that we have some multimodal PDF function, and these multimodal PDF functions, if you assign, for example, if you consider a histogram for that, then you have to keep the whole data in order to get the PDF as a histogram. And normally for the non-parametric PDF estimations, you need to have a bunch of data saved in the memory, and it's not good. It's actually computationally more costly than parametric methods. Parametric methods, what they do is actually they assign a PDF which is noun, for example Laplacian or the Gaussian, and for the Gaussian or Laplacian we know that we have, for example, two parameters. Based on the data, we can just, using the maximum likelihood, get those parameters as I already shown in the slide, the mu and the sigma, or the covariance. So that's how we get the parameters based on the data. So we have something between the parametric and non-parametric method, which is called the mixture of probabilities. The mixture of probabilities is a semi-parametric method of density estimation, the PDF estimation. Why it's something in the middle? Because that number of the PDFs that you want to mix together in order to represent the PDF of the data itself, the original data, that's another variable is added. So if the data is so complicated in the PDF case, that number of the components which are to be mixed together will increase. But on the other hand, it doesn't have the complexity of non-parametric methods. And it's not as simple as just the parametric method, which assigns one noun PDF. As an example, the Gaussian mixture is a very good semi-parametric method for estimating any PDF function. Assuming, for example, here, assuming that the PDF of the data is actually something like this blue one here, you can assign you can actually consider these two individual Gaussians with different means and different variances. And if you consider a mixture of these two Gaussians with some appropriate scalings, with some appropriate assignments, if you mix them together, then you would be able to get to this red explanation or estimation model, which almost perfectly fits to the real PDF of the data. Okay? So in this case, we have a multimodal PDF, which could be perfectly estimated using a mixture of two Gaussians. Practically, it has been investigated, and for many real applications, the PDF of the data in the real applications, we can just use the Gaussian mixture, but the different number of the mixing parameters. So we can, for example, for the case of speech, if we use, I don't know, maybe 16 mixtures can almost perfectly, they can actually fit to the vocal part of the speech. They could be actually represented. The PDF of that would be represented by Gaussian mixture if you use the 16 number of the Gaussians. Then it means you have, for example, 16 number of the mu's and covariances, and 16 number of the scalings for any of these PDFs. So these are the whole number of the parameters that you have to save instead of the entire data that you, in the non-parametric method, you have to save it. Why? Because you want to get the PDF out of that. And we know that if we have the PDF, in many cases, the estimation of, the expectations, the variances, and many other applications, like the MMSE estimator. For the MMSE estimator, if you have the PDF, then the MMSE estimation would be much easier. So knowing the PDF gives you a lot of information. So the PDF is actually, for a data, is something that gives all the information necessary for that data, random data. And PDF actually assigns for the random data. If you have the PDF, you can have the mean, you can have all the statistics. And if you have all the statistics of a data, you have all the information necessary to deal with that data. So Gaussian mixture model is motivated using this idea of density estimation and the semi-parametric methods. Assuming that this is the contour of distribution of a set of data actually it's a three-dimensional representation, but the domain is just exponent x2, and we have, for example, this kind of data contour. Then we see that this is very complicated, and you would not be able to assign a PDF, a noun PDF like the Gaussian or Laplacian or whatever like that, to get such kind of data. But it's so easy. If you use 3 number of the Gaussians and mix them together with some scaling, you would be able to actually assign and fit to the data and somehow model the data. And a good model is an advantage for every process. If you have a good model for some data, you'd better use it. The entire process would be so simplified. So here we see that if we use this Gaussian mixture, then you would be able to fit the data to this Gaussian mixture model, and you have the PDF of the data. On the other hand, you have the classes which the data are belong to. So it's somehow solving the problem of classification, or the clustering, better to say, is the clustering. So you have the class labels when you are doing the Gaussian mixture. In other words, you will assign those data which are actually generated from one PDF, one of the Gaussians, they are actually taken from that Gaussian, so they are actually shown with different colors here. So it's somehow like giving the labels to part of the data. So these are the advantages of using the Gaussian mixture as a model. Okay, let's see what Gaussian mixture is actually looks like. Gaussian mixture is nothing but the linear superposition of the Gaussians. So you have the data x, and you want to estimate the PDF of x as the superposition of k number of Gaussians. So this is the Gaussian. Each of these Gaussians contain a mean and a covariance matrix. But the proportion of any of these Gaussians, how much from any of those Gaussians should be used actually, is in this prior probability P of k. That's the proportion of each of these components. So any of these components, we have k components, Gaussian components, and you have the proportion of those assigned to those components actually. And we know that here the pk is a probability, so they should sum up to 1. So from here it's obvious that there is a big difference between the EM, between the Gaussian mixture modeling, for example, for class labeling, and the one we did in the k-means algorithm. In k-means, we are actually hard assigning the data to one of the clusters, the centers, the centroids that we had. But here, we are actually using the probabilities. So we are saying that how much any of those Gaussian components actually is responsible for generating that data, xi. Okay? So it's a soft assignment. Okay. We know that based on the sum rule, we can just generalize so P of x and consider it as a marginal probability of P of x and k when we sum up over the whole classes, k classes. So this, the right hand side is nothing but px and k together. So what we already have is the joint probability of x and k. If we have the joint probability of x and k, so it means that classes together with the probability of data and the classes together, then everything about the data is known. But when we don't have classes, so we have a missing information. So P of x, if x is observed, it has actually a missing part, and that missing part is the classes. We don't have those classes. So what we already have is P of x and k together. If x and k are together, then we would be able to say that, okay, if we have the parameters, then we would be able to say that, okay, this data is taken from this Gaussian. And that's the PDF for each part of the data. Otherwise, something is missing, and that's the class label which is missing. So we are actually trying to maximize the log of likelihood based on those unknown parameters, and we get the data x as an observation. Algorithm that we're trying to use is the EM algorithm, and we actually motivated the use of EM, but EM is not resort to Gaussian mixture. EM algorithm is a general algorithm that is iterative, and it's actually widely used in different applications, as I already mentioned, for example, in hidden Markov modeling and many other applications. So EM is actually expectation maximization. So the algorithm is compound actually. It has 2 steps. The first step, which is doing a kind of expectation, and then the second step, which is maximization. And you are alternatively moving between these 2 steps until a kind of condition for the convergence happens. Then the algorithm stops. The algorithm well, the idea actually goes back to the late 50s, but much of the investigation actually happened in the recent years. So let's pictorially see what EM does. And then I will ask you a simple question. So assuming that is again the data we have. The EM algorithm works like this. It assigns two Gaussians if we know that we have two number of the Gaussians. The same problem that we had in the k-means. Here we also have about the number of the Gaussians. So for example, we are trying to actually assign the two Gaussians and get the parameters of these two Gaussians together with their proportionalities, scalings. So we draw two Gaussians randomly, so with the mean and sigma, which are randomly generated. And they may, for example, be placed somewhere here in the data space. It has nothing to do with the data right now. But they are just been located something like that, because the means and the covariances, the parameters are taken randomly. So we do this, and we do the assignments. By doing the assignments, we get the new parameters. The new parameters are the mu and covariances, mu and covariances, mean and covariances. So when we do, so we have to move actually forward. Then we again do the expectation and assign every data point to every of these Gaussians, and then we re-estimate the parameters. We update the parameter estimations, we get new Gaussians. When you get the new Gaussians, then again you calculate the likelihood that this data belongs to this Gaussian and do the reassignment. The next reassignment, when it's done, you have to update the parameters and you get these new parameters, the new mean and new covariance. And you do that until convergence happens. And for example, after 20 iterations between the E and the M, E step and the M step, the convergence happens and there is no more assignment or no more change in the parameter setting mu's and covariances. So the algorithm stops here, and now it means that we have two classes, and bunch of the data here in purple is actually the one generated by this Gaussian with this mean and the covariance, with this probability, so with the proportional probability P of k, this one P of 1 for example, and these data are belonging to this Gaussian with this mean and covariance probability. So what's the difference now pictorially, what's the difference between this and k-means?
With k-means, you just have one parameter.
Great. So for k-means, we just took the centroids. There were no Gaussian around the centroid. But here, we assign covariances. So we have the centroids and the covariances for that Gaussian, because we know that every Gaussian can be represented by the first two statistics. So here we have two parameters, the centroids and the Gaussians, the covariances. And then we assign the data based on that. So now the point is, let's talk about the Gaussian mixture model and how it works. So in general, we have the data xi. I should vary from 1 to whatever, like n. And this data is actually taken based on some parameters, t, theta. And we said that we can generalize because we have the combined model, the joint model, when we have the data and the hidden variables, but what we observe is just the p of x. So it means that, here it means that the PDF of the data is somehow the marginalized version of the data and the hidden variable, which is zi, or the class label. It means that the probability of data I being taken from the class K or the Gaussian K. Somehow the class label K having the responsibility for generation of the data sample, for example, xi, given the parameters of these Gaussians that we have. It can be simplified to the right hand side. So we have the normal distributions because we have mixtures of Gaussians. So we have mixtures, K number of the mixtures with these scalings, and these are the Gaussian parameters. The probability of class label, the probability of data I being taken from class K given those parameters is called these priors, pk. And this is the one for the Gaussian, the data which is actually taken from a Gaussian. And the set of parameters that you have are pk, mu k, and zk. For k, 1 to capital K. And this is how it looks like in two-dimensional space. Now you want to do the maximum likelihood fitting. You have to, you have a set of parameters. You have to assign those parameters to, get those parameters based on some optimization method, which we use normally, the maximum likelihood. So somehow EM algorithm is generalization of the maximum likelihood when you have some missing data. So generalization of the maximum likelihood method when you have some missing data is called EM. Maximum likelihood fitting. So we have to do the maximum likelihood. There is a notion, a new concept that rises actually here, and it's called the responsibility, and it's shown by RIK as an indicator function. What responsibility means? So RIK is how much responsibility the cluster K takes for the data I. The amount of responsibility that cluster K takes for generation of the data xi or I. So it can be shown also by this indicator function. Now if you want to estimate the priors, the pk, which we already saw here, that pk is the probability of data I belonging to the class K given the parameters, it can be easily shown by this. So you have n number of the data samples, and pk would be easily drawn using taking the average of the responsibility of every class K for the whole data. So to sum up the whole responsibilities of each class for the data, normalized by the entire number of the data samples that you have, and that would be what you assign as the P of K. So it's RK over N. And then for the mu K and the sigma K, the covariances, in the same way, you're just giving the weights, the responsibility weights for each data sample. So you have, just look at the problem as the clusters, as the bunch of data which have the same property and they're gathered together. So for the mu K, you want to find the centroids for each of these classes. These centroids should be actually calculated in this way. So you have the data samples I, you have to calculate the responsibility of any of these samples. You want to get the centroid of class 1. Get all the responsibilities of the data samples times the data. So do you have the data xi for any of those data? How much this class K gets the responsibility, accepts the responsibility of that data. You sum up all the responsibilities for that class with respect to the data that you're calculating actually, and then normalize it by the entire responsibility of that class, and that will give you the centroid of that class. And the same thing for the covariance. So how much you are having a bunch of data, they are all together, they are somehow crunched together. So what we're trying to do is how much energy of this data that you are calculating is actually close to the energy of that class. So you have the responsibility of that class times the energy of that data, normalized by the entire responsibility that that class can take, and you just subtract the mean energy, energy of the mean of that class out of that, and this is actually intuitively telling you about the covariance of that class K. So initially these parameters P of K, mu K, and sigma K, intuitively they can be actually extracted out of these, and there would be the derivations for that in the book. It's in more detail. It takes some pages maybe to get the derivations completely, but you can also intuitively explain about how these could be derived without going through the derivations. So the GMM, we talked about the GMM and the maximum likelihood fitting of the data. So the parameters we actually got for that GMM, but the EM algorithm actually how it goes for the GMM is in this slide. So in the ES step, we're doing actually the expectation, which is actually soft responsibility assignment. What we're doing in the first step is calculating those responsibilities, which is the probability of class K being the responsible class for the generation of data xi, based on the parameters that we have. So we assume that xi is given. If we assume a theta to be noun, something, then how much is probable that class K has generated this data xi? Then this is called the responsibility, and it could be calculated based on the Bayes rule. It could be easily calculated here. So if it's the posterior, you can just change it to the prior times likelihood over the evidence, and that's what finally comes out. So it's the prior of that class times the Gaussian of that class, and it's normalized over the entire classes. After calculation of the ES step, so in the ES step you fix the theta and you go for the expectation. So you go for the responsibilities. You calculate this probability. You assume something. You initialize with some random theta. By initialization, randomly, you make this calculation, this expectation, and then in the next step, you assume that this responsibility is fixed, and you go for the likelihood. So the other way around, it's just like, alternatively moving from one step to another, then coming back, and trying to update your belief about what you're doing actually. In the next step, we are updating the theta. Assuming that the responsibilities are taken fixed, we are updating the pk, mu k, and sigma k as we mentioned here. So you have the responsibilities now, then you calculate the pk. You have the responsibility and you have the data, calculate the mu k and calculate the sigma k. And these are alternatively done, iteratively done, until some kind of convergence condition happens. And that's how EM works for the GMM algorithm. Intuitively, it's called, before going to the other stuff, let me explain about that slide is taken from Arta. So it's intuitively resembled to they call it as a hill climbing algorithm or the coordinate ascent. So whenever you hear about the coordinate ascent or hill climbing or coordinate ascent, they are actually representing the same thing, the same idea. And what is that idea? It says that you get the set of parameters at time t. T can start from 0, just initialization of the algorithm. You get some theta, some parameter set, randomly chosen, as in the pictorial graphs that we saw that we have two randomly generated Gaussians. Getting that theta, you actually get a function, which this function is nothing but the likelihood. The likelihood of the data based on the likelihood of the class being, the class K based on, for example, the data that we have and these theta parameters which are already taken to be fixed. This likelihood function shows something like this blue curve. And for example, this hill climbing, this one is the real of what you have to get. The real likelihood of what you have to get. So by putting theta initialization, you get this blue one, and you get the maximum of this blue one. So the maximum happens here. Now you put your next theta to be here. Then you draw the likelihood again based on these fixed values. You get another one here. You update your belief about the theta here. You calculate the function again. The likelihood function gives you here. You get the maximum here. So you put the theta to be here. You change it, you get this one. You change it, you get this one, until you get here. Then afterwards there will be no change. So the theta value starts to almost be fixed without any changing. That's the point that the EM algorithm stops. That's why it's called the hill climbing or the coordinate ascent algorithm. So this log likelihood of the data based on the parameters is actually doing this kind of pictorially shown task. So there are so much details about the EM algorithm, and we have to skip through most of them. But what I can mention here is there is another view for the EM algorithm by itself. So let's review what we said in the lecture so far. We said that we need, for the clusters, we need the class labels. One method was the K-means algorithm. It does everything in a hard thresholding way. We have something softer, and it's called the EM algorithm. But beforehand, we are talking about the idea of the Gaussian mixture as modeling of any kind of PDF. For most of the data, we have a very complicated PDF, so it's better to have a kind of, more flexible modeling of PDF, which is called the mixture of distributions. And mixture of Gaussian is the most prevalent mixture of distribution method for the PDFs. So by assigning different means and covariances to different number of the Gaussians with an appropriate number, then you can get the PDF of any kind of data with a very good approximation. For the Gaussian mixture, we have the problem because we have all the information. We can actually calculate that likelihood of the parameters if we have the class labels, but we don't have it. So there's something missing. In order to get the maximum likelihood for those parameters in the Gaussian mixture, when we have some missing data, and the only thing which is available is the joint probability of hidden variables together with the data, we need to marginalize everything. For that to work, we need to make a kind of algorithm like the hill climbing one. So we should take the parameters noun, and then by fixing that, assuming that is fixed, jump to the likelihood, calculate your likelihood for the parameters, calculate the likelihood of the data to be taken from the parameters, give the assignments of the data to those mixtures, and then to the components, and then alternatively move between assignment and parameter updating, until it converges. That's the idea of EM, and that's what motivated us to talk about the EM algorithm. And we explained that the EM algorithm intuitively can be driven as we showed in the previous slides. But then EM algorithm is actually more general than that, and it could be seen as a kind of latent variable modeling. And there is another view of EM algorithm which can be seen based on what I showed in the hill climbing method. What we're trying to do is we're trying to maximize actually the lower level of the likelihood, so the lower bound of the likelihood, and that's another view to the algorithm, EM algorithm here. The graphical model for the for actually the EM algorithm is like this. So you have a hidden variable, you have the observed data, and there is a relation between this hidden or state variable and the data, like this. That's the graph that represents an EM algorithm. So I wonder if I talk about the details of calculations, maybe it's getting too complicated for you. So maybe it's better just to talk about that intuitively. I think so far the idea of EM and the GMM is clear for everyone, unless there's any question.
I don't understand the difference between EM and GMM in the sense that
Now, GMM is a model. EM is the method to solve that model. EM is a technique that you're solving. GMM is
a mixture of
Gaussians. It's just a mixture of Gaussians.
And we use it in the EM.
For example, you say that the PDF of this data is taken from a Gaussian. Now you say that the PDF of data is taken from a mixture of Gaussians or Gaussian mixture model. Now in the normal case, you use the maximum likelihood for the simple Gaussian. Here you have the mixture of Gaussians. You cannot apply the simple maximum likelihood. You apply EM.
Okay.
EM is the generalization of maximum likelihood, as the GMM is the generalization of the Gaussian, multivariate Gaussian. You got it?
Yes.
Any other questions? So we changed this incomplete data, which is the data without the class assignment, to such kind of data by using the GMM algorithm, the GMM method. So it is so probable that I will give you a simple project using the GMM algorithm to model, for example, parts of speech like the voiced phonemes or unvoiced phonemes, and then to be able to recognize the test data which part of the data is belonging to the voiced and which part belongs to the unvoiced. Or we can do the same thing for speaker identification. For example, you train the data for different speakers, and then you get the sample test data from one of the speakers, and then you should be able to recognize who is the speaker of this. So if you have the names, for example, Mary, James, Michael, these are the generators of the data, then you would be able to recognize the data which you have been given by as a test data, then it's generated from which of these people. Okay?
Also to distinguish male from female, we can use it.
Of course. There are so many properties, just specified for the male, like the pitch frequencies for the male, which are much less than the pitch frequencies for the female. It normally is like that, and the formants also. But you can find some other features from the data, or you can train maybe a neural network when there is a kind of when you have not a clear mind what kind of feature you have to extract, then you can probably assign neural network like the RBM, the Boltzmann machines, in order to extract out the necessary number of the features from the data. That's the topic of the sparse autoencoders, or the autoencoders, that I will talk about that in the ESS part. The autoencoders, you can use it for extraction of the features when you have no clear mind. That's what should be those features. But those features should be representative. When you do the neural network, then the features would come out of that is representative when you have the training data. So the explanation of the GMM and EM and K-means is over now. There are some derivations out of that. They might be a bit boring if I go through that, and I cannot stop in less than 30 minutes if I go through that. So I will put everything together with the auxiliary notes in the website, and you can take it, but it's just for your knowledge if you want to have more information about that, and if you are not getting bored by doing some math calculations, you can go through that. And if you have any questions, then afterwards you can just come to me and I can ask about how these derivations have been made. But probably in the class I will skip explaining about all this information. The only thing that I want to mention is that we have this log likelihood. This log likelihood in general, it can be represented like the log likelihood based on some other PDF, which is Q, and it's noun, plus a Kullback-Leibler divergence between Q and P. Is there anybody that doesn't know about the Kullback-Leibler or KLD, Kullback-Leibler divergence? You don't know that? Okay. There is a measure that this measure is called Kullback-Leibler, KL, or another abbreviation KLD. It calculates the difference or the distance between two PDFs. So we have distance for two vectors, distance for two scalars, distance between two matrices, and here we have distance measured between two PDFs. Q and P, if you have these two PDFs and you want to calculate the distance, how much these two PDFs are close to each other or not, you can take the Kullback-Leibler divergence. So in information theory, or the basics about the information theory or data communication, you will go through that. It's so simple. Is anybody knowing the meaning of information? Entropy?
Uncertainty of information. How disperse the information.
Uncertainty is actually represented or quantized by a value which is called entropy. So the amount of information is reversely proportional to the probability of that data. So the data which is more probable to happen, which has more probability, has less information. And the data which has less probability, when you get it, then you have more information about the data. Yes? So that's a measure which is called entropy. And the representation of that is actually, I don't want to extend your course because then I have to go to other courses. But then you have, for example, for any data, minus P, log of P, is actually showing the information in that data. That's the entropy. It's called H. So if you have data xi, H of I is actually the amount of entropy of the data is like this. And this minus is actually coming from Pi log of 1 over Pi. So how much probable the data is and how much information we get from the data, which is actually proportionally in the reverse order. So when you say that KLD between two P and Q, these probability distributions, it actually means that you're having, for all the data that belongs to the P and Q, you're actually taking the log of P over log, is actually log of P over log of Q times the log of P over the entire data. So the relation is something like that, but you don't need to go through that. The KLD is just the measure of distance between two probabilities. That's all. So what EM algorithm does, well, actually here is written. So you have the, for example, P and Q. If you are here to look for how much Q is close to P, then you sum actually over all the latent variables, Q and the logarithm of P over Q. That's the KLD. And here is actually the likelihood function of the Q itself. And what it actually does in the hill climbing algorithm of EM, it says that you calculate the function for the log likelihood, and this is the real likelihood of the data. So there is a distance between these two. By iteratively going from EM, and assigning and doing the maximum likelihood, you're actually somehow improving the level of that log likelihood of Q such that you are more minimizing this this KL divergence, or minimizing the distance between the Q and P until it becomes zero. So it actually tries to get closer and closer to the zero, and whenever it becomes zero, it means that Q is exactly P. Okay? And does that in the sense, the hill climbing method that I already shown you. So I don't want to go through the details of the calculation, but I can put them, and there are very good explanations. Well, not so much in internet you can find about that, but I will try to enrich my slides. So I add some additional slides, but these are just for your knowledge. You don't need to learn it. It's not necessary for your exam, but for your just information, you can have it when you can use it. And then we will actually upload some examples for the k-means for EM algorithm and the GMM, and then probably you will also do some kind of homeworks using the EM algorithm and the GMM method for some data. Any questions?
So like the scope of this lecture with respect to examination would be the definition of the algorithms, and the summary would be problems based.
Just the simple things that I mentioned. So, many of these topics that I bring up in the course, they contain a rich theory behind. I don't have enough time to go through the rich theory, and sometimes if I go through part of the theory, it's much worse. So I have to somehow manage what kind of material I'm going to explain here in the course. If I, for example, I can just go and start, for example, there are a lot of things, more than 40 pages talking about EM and the GMM and so on. If I go through that, if I stop in a point, that point should be a reasonable point. Otherwise, you will be confused. So you see that, okay, so far so good, but then what comes next? And I cannot stop in that point. And we have just 1 hour something. So I have to manage to which point, if I explain the idea, you will be not confused. You will get the entire idea. You will be able to use it in practice. And you get the leads if you want to continue with the mathematics, and I will provide it, and you can go through that. Otherwise, if I go to another step, which is not a good point to stop with, then you will be confused. So these are the topics. The scope of this lecture was about k-means, GMM, and EM as 3 core techniques in the machine learning, which could be applicable in many areas, like the hidden Markov model as a very prevalent model. It's widely used in anywhere that you can imagine. And in order to calculate the parameters in the hidden Markov model, they should use EM. Now you know EM, you know how to extract those parameters, but for the proof why this kind of explanation is right, you need to know the math, and I don't go through that. But I will provide you with the material. You can go through the materials. And if you have questions, I can give you the answer. In the exam, the only intuitive things that I explained, you're not going to prove something. For example, I will mention the difference between k-means and EM algorithm, the GMM, the EM algorithm for the case of GMM, what you will do. What is the difference? Or explain the EM algorithm for the GMM in brief. So you just explain E step is this one, and the M step, which actually calculates these parameters, updates the parameters in this way. That's all. And then it clusters the data. That's for the exam. And for most other topics that we bring up, and they are having this much rich mathematics, the exam would be just like that. Just the intuitive idea, if you have got it, that's all. We don't want to go through the details. Okay.